speaker. Jon Lehmkuhler is a commercial manager for Great Lakes Solutions. He's going to talk on bromine derivative materials. So welcome, Jon, please.
Okay, thank you. Thank you very much. I hope everybody can hear me in the back there. So if not, hold your hand up. Every time you have to speak, right, you want to come up with some sort of opening that's good. And I think this time I struggled a little bit more with what to come up with. But, you know, you think about all the things happening with the electric power industry, fuel regulations, capital benefit, you know, all the other things. You know, Jon mentioned the phrases, right? And all I kept thinking of was big things, big challenges, right? Big. And that didn't help. I still was struggling. So, like most things, my 12-year-old daughter, my 9-year-old daughter helped bail me out. The 12-year-old found something, and the 9-year-old liked it so much she started telling everybody. So I thought, hey, I'll go with that. And it's, you know, thinking along the lines of big things. There was a teacher teaching animals to her classroom, and she was talking about whales and elephants and all the big things. And one of her students raised her hand and said, "Well, couldn't a whale eat a person?" And she just adamantly denied that. No, whales don't have a big enough throat. They couldn't swallow a person. It couldn't happen. Well, the little girl wasn't going to give up. She said, okay, but, you know, there's a story there about Jonah, and he was eaten by a whale. And the teacher said, okay, try and get her pupil back in line. You know, it still can't happen. And the little girl said, well, you know, when I go to heaven someday, I'll ask Jonah, and he can tell me. And the teacher wasn't going to let it rest. So she said, okay, fine. What if Jonah didn't go to heaven, went to the other place? And the little girl said, well, then you can ask her. So that was my opening, so I'll give them the credit for that. My topic here today around bromine derivatives is kind of a look at, there's been more bromine being used now for mass compliance with mercury control. There's been a lot more work done. EPRI's doing a study with URS or ACOM to look at some of the impacts of that. And I'm going to give a little summary of that work, as well as some corrosion studies and some testing we did for things for the handling units. So hopefully this will give you some information that will help. We do have all the studies and everything in our booth, so if you'd like to come by and pick up copies, that's more than fine. They're there for your availability. Great Lakes Solutions is a part of Chemtura. We are a $2.2 billion corporation. Global corporation, more than 2,700 employees, and basically this is the way we're broken down right now. We are urethanes in our petroleum additives group, Great Lakes Solutions, which is legacy Great Lakes Chemical, and then we also have our organometallic specialties group as well. So moving on, mercury control technologies. One of the things that has been determined in the past has been that bromide, or having a halogen available to do oxidation, is important. And a lot of those technologies have been developed using bromine in order to do that. It's available as far as production quantities, and its efficiency is good as well. So when you look at a lot of the technologies out there, many of those do entail using bromine. The bromine, basically, I think most people are familiar, but I'll go through it fairly quickly. The bromine is entered either onto the coal or into the boiler for the most part. It can be added in different parts of the system, and basically that's where that is done. Basically, again, the focus is to oxidize mercury, to get it in a form that can be captured downstream. There's technologies that have been developed. There's intellectual property out there. I encourage everyone to look at that. Make sure you're following all intellectual property restrictions. And then EPRI has done a survey as well. So again, I'll give you a little more detail on that later. This is an operating and capital cost-effective way of doing it. And for the most part, you are basically doing this when you're using coals that are lower halogen content. So you're adding the halogen where it's not already present. And then there's been some studies done as well looking at the efficiencies, which are quite good. When you look at our product, which is geobrom, which is a calcium bromide product, what are some of the benefits? Number one, if you're using an SCR, getting oxidation through an SCR, having that bromide takes a little bit of that burden off your SCR. You can reduce some of your carbon costs. So if you're using a brominated carbon, using a combination of calcium bromide with a plain carbon may be a better operating cost idea for you. It may allow you to use less carbon, which would reduce the risk of fly ash. If you're selling a fly ash in the market, it would reduce the risk of that becoming an issue. And then you do also, if you have particulate control devices that are fairly loaded, this would help reduce carbon use. Carbon use lower would help reduce having to do much more to expand the capacities of your particulate devices. If you're using other co-benefit technologies, having that little bit of extra oxidation will help you as far as capture downstream. So if you are on the borderline or you do a lot of things to change your plant, whether it's fuel blending, whether it's how you operate, load, everything, it gives you some flexibility to make sure that you're still in compliance with the MATS regulation. The systems for calcium bromide are fairly simple, and the equipment is basically out there. A lot of the equipment you can use, like blind FRP tanks. The big things you have to remember with calcium bromides in particular is the density, the crystallization point issues with that, the temperatures. But all of that can be dealt with fairly simply. You can transfer by pumps, you can transfer with pressure. You've got a lot of tools available to you to deal with these systems. Again, the big thing there is density and crystallization temperature. If you're in a colder area where you would potentially be, the rule of thumb is as long as you're staying about 10 degrees above that crystallization point for your normal conditions, you're going to be all right. But you could install a recirculation line to help with that, or if you need it even in very extreme conditions, a heat exchanger or something, a small one that would provide a little bit of heat input as well. Looking at the balance of plant and corrosion studies, which is the next part here, again, a quick summary of the work that EPRI has done, and many of you probably have seen it at other conferences, seen it put out there. I've got the references at the bottom. But for the most part, they looked at a number of units. Out of the 83 they looked at, 14 were only really doing parametric testing, so they pulled those out and looked at the other 69. And of those 69 units, 45 were basically Section 45 units for Section 45 tax credits. 19 were meeting state or other regulations, and then 5 were being used in a combination. So a lot of what's been done with bromide at this point has been driven, obviously, based on the timing of MATS from the Section 45 perspective. Basically, they really haven't come to any hardcore conclusions yet to say bromide is or isn't the issue at this point. There's a lot of things going on within a lot of these plants. They did look at all the potential areas of concern, which would be the coal handling, the furnace, the air heater, the other pollution control devices, and the ductwork as well. Most of the corrosion, as you can see, is in the air heater. And that's where you're getting your temperature changes, right, that you're going to have the potential to have acids and things condensing out. And there were 2 units actually in the study that the corrosion was not solely attributed to bromide. One of them was already operating below sulfuric acid dew points, so they knew that was going to be a concern. And another one, it was prior to the bromide addition, they were already seeing some corrosion as well. There are other contributing factors with the Section 45 units. They also had another additive that contains chloride that could be contributing as well. And when you look at things like air heater leakage or your up and down, your loading balance, there are other issues there that are going to increase your risk of temperature changes that could lead to acid condensing. They tried to break down the data that they had of the survey to see are there any smoking guns as far as what could be causing the problem. One of the things they looked at was coal type, and basically where they did observe corrosion, they were all PRB units. Now there were some PRB units that did not exhibit corrosion, but for the most part where they saw corrosion, these were mostly PRB, low halogen coals. The ones where they didn't were basically all eastern bituminous or Illinois basin, so higher units. The thought there maybe is that if you're already dealing with the acid problems because of your higher halogen coals, then you're maybe a little safer than when you're not, when you're operating with low acid coal. With the coal handling equipment, pretty much nothing really was observed prior to bunkering, and a very small percentage was when they were adding it to the pulverizer. The air heater, again, this is where most of the corrosion was demonstrated. Most of it was at the cold end. So again, the question there is what's going on with the operation of the unit as far as temperature. But basically, the other part of that they found was that there really was no corrosion exhibited when they used enameled baskets. Now, they didn't have enough data to really recommend using that, but for the most part, with our experience as well, dealing with hydrobromic acid and other materials that are like that are corrosive, as long as you do have a reliable coating that's being used in the right application, that will help with corrosion issues. At the boiler, really didn't see any problems there. You wouldn't really, at those temperatures, necessarily expect to. But where they did see a couple weld issues, it was analyzed that chloride was there, not bromine. So in that particular instance where they did see that, they saw chloride present. When you look at the bromine additive rates, now this is one that was, again, a little kind of a mixed bag of information. They saw that the loading, for the most part, didn't really come in line with what you would expect, that higher was worse and lower was better. And then again, when you looked at some of the very high rates of the higher halogen coals, that was less of an issue, where they did not demonstrate corrosion. So the jury is still kind of out on that one. The Section 45 additives, as well as activated carbon added upstream. When you add activated carbon, if you don't have enough soot blowing and you have solids that are settling out on your surfaces, they're going to grab onto the acids or potentially hold it closer to the surface. Now you're going to have a better opportunity to have corrosion in those systems. And then the air heater, the material construction, again, enameled and coated things basically seem to work better. The corrosion mechanisms you're looking at here is either direct condensation of hydrobromic acid on the surface. You potentially have hydrobromic acid contributing where you've already got sulfuric or hydrofluoric acid already condensing. And then you have salt formation where you could have a situation in changing loading where you have a higher temperature and a lower temperature, and then you get some salt to precipitate out on the surface. Then you could also have the gas corrosion of HBR. Typically, you really need much higher temperatures than where we were seeing corrosion here. The corrosion studies we did, that's kind of the summary on the EPRI piece of it. The corrosion studies we did were working with EPRI, were focused more on the handling equipment, handling calcium bromide, and what you would need to do as far as introducing it into the system. We did 90-day tests. We did look at welds. We looked at basically carbon steel, stainless steel, and some duplex. And then we looked as well at just liquid submersion, just vapor, and then a mixture to kind of see if you get anything involved with the surface. And again, this is all based on materials and construction for the right application here. To give you just a quick summary, and again, if you want more of the details, please feel free. They're out there available to you at our booth. Please feel free to pick them up. But for the most part, when you look at the corrosion, the total liquid test here, the carbon steel was the one that really demonstrated the most issue. And even so, that's still around 1.5 mils per year as far as corrosion. So still fairly low in most cases. When you break out this lower piece here to the bottom graph, you can see that for the most part, these are all still very low corrosion rates. Definitely with a little bit of temperature, as you would expect, you get a little higher corrosion rate. And then the surface impact here, I know that's probably a little bit difficult to see, but for the most part, this was really the carbon steel was the only one that really demonstrated any kind of major pitting or any other corrosion evidence. Looking at the vapor space, okay, this is basically no corrosion whatsoever. These limits are incredibly low when you look at it even across the board for even carbon steel. The solutions basically picked up absolutely no color, and basically all the coupons for the most part look very clean. So when you're looking at the vapor space, it's really not the vapor that at these temperatures that you're having issues. You're not creating a lot of HBR or something out of the solution that's going to that's going to impact where the vapor is coming in contact with the metal. Now, on the partial corrosion, and these, I will say, these solutions look a lot like what the liquid tests look like as well, so this was not a surprise. And basically very interesting, with half the coupon in the liquid and half in the vapor, you also ended up with about half the corrosion rate. So basically what you would expect. There was no major impact at the interface, and for the most part, even still, the corrosion rates are still fairly low, less than 1 mil per year. You can see that there was some pitting and some evidence on the surfaces, but for the most part, again, the duplex, the stainless steel, those all performed very well, and even the carbon, for the most part, given the application, did fairly well. A quick summary. I mean, the benefits of using bromide are fairly clear. They're low in operating and capital costs. The reduced risk of fly ash, so there are some other things that gives you some leverage to pull in your plant for your compliance plans. And it allows you to adapt to changing conditions. So if you have a plant that's got a lot of things going on all the time, it gives you the opportunity to do things that you may not be able to do if you only have one lever to pull. Bromide is being investigated, and there's still more work being done. So there's, I'm sure, more reports that will come out. I think if you keep your eyes open for those, there's more data coming out every day. Nothing has really been attributed totally to bromide. And then there are some other things going on in the plants, right, where you have the indication that it could be temperature and just dealing with a different environment as far as what you have coming out of that boiler. Air heater temperature is a big focus, and soot blowing if you're adding carbon upstream, as well as if you enable your baskets to do some things around the materials of construction, could also help with any issues you might see. And then again, the work we've done looking at calcium bromide with the systems you'd be using to handle it have not really demonstrated much impact whatsoever as far as any kind of significant corrosion rates. Again, very much dependent upon what your application is and how you're using that piece of equipment for the most part, though nothing really significant. So for the most part, that's all I have. Again, I encourage you, if you'd like to see the data, the hardcore data, there's much more detail in our brochures we've got, and you can use that then further as what you're trying to do to plan for maps. Any questions?
Thank you. Are there any questions? See one up here. You can get a microphone.
Yes.
I don't see any mention of the flue gas moisture level. To me, when I see PRB recycling it, I think of a high moisture level in the PRB, and I know that dew points are definitely related to the humidity level, or moisture level, percent moisture vapor and gas. Has anybody looked at that? Maybe the answer here is soil, because you have the right level of moisture in the PRB fluid, and you can get a good reaction, maybe sort of like capture that.
You mean to capture the aqueous gas? Yes. And that's, there was mention in the effort report about the moisture levels of the coal. You bring up a good point. There was nothing really stated as far as correlation in any of the data. So I do know they were looking at some real hanging some real coupons and getting some tests to see what that is, but I did not see directly direct information as far as the moisture.
Probably look at that. You want to change the level of temperature.
The one thing that they definitely did demonstrate was the difference between the BRBs and the bituminous. So there is probably something going on there, but enough data to say that you can put your finger on it. I don't think they have that yet. It's a good comment.
Other questions? Well, thank you so much.
Thanks.